Assalamualaikum warahmatullahi wabarakatuh. Hi everyone, my name is Andre and
I am Farrel.
in this project video, we will present about our project that called Analysis of Microthermal Signal using HVSR method for mapping the soil vulnerability in Semarang, Indonesia.
Before we dig deeper, let me explain the background of this project. Semarang's rapid expansion has pushed development into suburban areas such as Gunung Pati, a hilly district with steep slope and its vital water catchment function. Its proximity to city centers, educational centers, and major roads make it a prime area for growth, but uncontrolled land conversion threatens its ecological balance. As agriculture gives way to urban development, the risk of erosions, landslides, and reduced water absorption increases. To ensure sustainable planning, microthermal surveys are conducted to map land vulnerability, providing critical data to mitigate disaster risk while supporting responsible development.
The problem formulation of this project are: how can microthermal waves be passively recorded in Gunung Pati area Semarang? How can microthermal wave data be processed using the HVSR method? And the last one is, what is the distribution of soil vulnerability in the Gunung Pati area Semarang?
And the objective of this project is to passively record microtremor waves in the Gunung Pati area in Semarang, and identify key parameters of microtremor waves and analyze them using HVSR method, determine the subsurface structural conditions of the Gunung Pati area, and create a soil vulnerability distribution map for the Gunung Pati area.
Of course, you have to know what is microtremor. Do you know what microtremor is? Microtremors are small continuous ground vibration generated by various sources like traffic, wind, and human activities. They represent natural harmonic soil vibration trapped in surface sediments and influenced by subsurface layers. The characteristics of microtremors reflect the local rock properties, making them valuable for soil structure studies and investigations. The tools and material that used in this project are Hydraulic ME series Astra seismometer set. It consists of sensors to record the ground vibration at measurement points, connecting cables to connect the seismometer to the digitizer, and the last one is the data logger to convert analog signals recording into digital signals.
Then we have the GPS, used to determine the position of each measurement point.
Next one is the compass, used to identify the north direction when setting up the seismometer.
And last, we have the laptop, used for data acquisition and data analysis. The research was conducted in January of 2025 in the Gunung Pati area of Semarang City. Measurement points were located near hilly areas or slopes utilized for infrastructure development.
The data collections begin with a site survey to determine the measurement locations. Microtremor measurements are taken in a location that is far away from roads, trees, buildings, and artificial vibration. The equipment is calibrated and the data is collected during the day on the original soil surface at surveyed point, with each measurement lasting for 30 minutes.
After measurements and data collection, processing is conducted to obtain the horizontal to vertical spectral ratio. Microtremor data, including NS, EW, and vertical components, is analyzed using geopsy software to determine amplification and natural frequency. To HVSR analysis. Filtering removes noise, while windowing is like signal free from anthropogenic interference. After measurements, the data is processed to obtain a horizontal to spectral ratio using geopsy software. Microtremor data includes three signals: NS, EW, and vertical. Noise is filtered out and windowing selects signals primarily from soil vibrations. The analysis determines amplification values, natural frequencies, and seismic vulnerability index. Additionally, ground vibrations acceleration is calculated using earthquake magnitude, soil period, and epicentral distance. These values help assess seismic risk and ground stability, or GSS.
The next step is calculating the seismic vulnerability index, or KG, followed by maximum ground acceleration, or PGA, using earthquake magnitudes, soil period, and hypercentral distance. Finally, ground shear strain, or GSS, is derived from KG and PGA values. The study area center of frequency values range from 4.89 to 12.72 Hz, with high frequencies over 8 Hz. Dominating Kanri, Pungangan, and Sadeng, indicating hard compact rock with a thin surface sediment layer below 5 meters. With amplifications, values range from 1.13 to 6.18, with most locations showing low amplification below 3, suggesting stable subsurface conditions. However, measurement point into Sadeng exhibits high amplification over 6, indicating the presence of softer rock, which may be more susceptible to seismic activity.
The seismic vulnerability index in the study area ranges from 0.13 to 7.81, with most locations having low vulnerability, which is below 3, indicating relative safety from land movement. However, measurement point 2 in Sadang shows a high index of above 6, suggesting instability and potential structural damage during earthquakes. This area consists of tufaceous sandstone conglomerate and volcanic breccia from Damar Formation, or QTD, which is prone to landslides. Additionally, it is located near a normal fault zone at the boundary of Karek, TMK, and Damar, or QTD formations, increasing the risk of land movement. Given these conditions, the Sadang area is more suitable as a green zone rather than infrastructure development.
Natural frequencies in the area range from 4.89 to 12.72 Hz, with high values in Kandri, Pongan, and Sading. The area classified as soil type 4 features as hard rock and thin sediments. Wave amplification mostly stay low, except near Sading measurement point 2, which has higher value. The seismic vulnerability index range from 0.13 to 7.81, with the Sading showing higher vulnerability index.
Peak ground acceleration value range from 7.79 to 12.74 cal, indicating a moderate to high seismic risk. Ground shear strain values suggest low strain in most areas, but higher values in Sading indicate a higher risk of building cracks during strong earthquake. That's all we'll be presenting today.
Thank you for listening, and sorry if we made any mistakes.
Wassalamualaikum warahmatullahi wabarakatuh.